Good, okay. All right. Let's start discussing what you have done. So, what's the first thing to do in this problem? We see, I mean, when we read the problem, what do we understand? We want to find a prime number. Uh, we want to find a prime number, and modulo this prime number, we want to choose a sequence of numbers which satisfy that every consecutive four of them, when we multiply, these products go like 1, 2, up till k, which is the last number. So we want to choose the sequence of distinct numbers modulo p, which satisfy this congruence relation modulo p. We want to choose p so that we can choose these numbers modulo p. Of course, p has to be large, right? K is given here. K itself could be large, but p should be larger than k, much larger than k, because we want to choose this many distinct numbers modulo p. This is the thing. So here is what we understand. The first important thing is that we formulated modulo p. These are the conditions. Now, what are these? Now we treat these numbers as these are just values modulo p. And then once we have the value modulo p, non-zero value modulo p, we can, of course, it corresponds to a particular element in this set from 1 to blah blah p minus 1. So here it's maybe a little bit good to talk about what is modulo p, to talk about the algebra of mod p and the structure, in the general structure of mod p, mod n in general, okay? So I want to open a new page here. Okay, Karim has also joined, right? So let me put this as a title, mod n. So how would you describe what is mod n? Okay, as a system. A mod n is a number system, right? A number system. Consisting of how many numbers? This is by itself a number system. What do I mean by a number system? Okay, number system is a very loose term that I'm using here. And there are more precise terms in abstract algebra, of course. What I mean by a number system is something like, okay, integers. Integers is a number system. Rational numbers, this is a number system. Real numbers is a number system. Uh, Complex numbers is a number system. Mod n is another number system. What I mean by a number system is, at the basic level, it's a set of elements, but there is algebraic operations in these elements. There is addition, subtraction, there is multiplication, and possibly there is division, depending on the divisibility. Such things have special names in abstract algebra. So when you have addition, subtraction together with multiplication, this is called a ring. And then, depending on how much division you have, there are notions of, integral domain, field, etc. So these are various concepts in abstract algebra. I'm not getting there, but well, for example, we can talk about matrices also as a number system because they also have their algebra, which also forms a ring. But for now, I'm just focusing on mod n. I want to, without overloading you with too much abstract stuff, I just want to instill this concept to you that mod n is a number system by itself, consisting of n numbers, finitely many numbers. So this is different from the other number systems, like integers, for example. There are infinitely many of them. In this sense, it is different, but it has its algebra. Now, sometimes we are tempted to say, so let's kind of be a little more correct than usual. We can represent these numbers by 0, 1, and -1. But notice that I'm using this word, we can represent. I'm not saying that these are the numbers, modulo n, okay? And there is a big difference here, which when I was an Olympiad student, I was not appreciating this. I really learned this much later in my life. I was always hearing this whenever I saw a description of modular arithmetic. It says, well, they usually refer to the other representation, which is mathematically more sound but a little harder to understand. And I was always curious, why do we need that kind of thing? We can just represent the numbers by this. And so when you don't know about the other representation, and when you just only know about this one, later on, when I learned about this stuff better, I realized that this kind of cuts your perspective. It's good to know about different ways of representing it. Do you know what I mean by other representation? And maybe you may know about it, but you may not think that it's another representation. Well, basically it is this. Instead of saying 0, well, okay, let me not just keep talking. So I need feedback from you. Obviously, this is probably the representation of modern in your minds, right? Do you agree?
Yes.
Yeah. So when you think of modern, so these are the numbers. Okay. So, but are you tempted to say, for example, that this is a subset of integers? Something like this. Can you kind of say that?
Sorry, I didn't get what you
I
mean.
mean, can you kind of say that mod n is a subset of integers?
Yeah.
So this is not a nice thing. So this is I tricked you. I intentionally tricked you, okay? Because I know this is the reason I'm asking you this question is because this is how I used to think naively, when you just as an Olympiad student, when you learn about this stuff. This is just intuitively how you get to think, but later, as you realize some of the nuances better and better, you find better ways of thinking. It's not a good way to say that this is a subset of integers. You can use these particular integers to represent the n values, modulo n, but these are just representation. And instead of 0, if you use n, it is also a representation of the same value, modulo n. Now you might say, what is that value? Well, that value is what it is. Do you give it a name? You may or may not give it a name. Even if you give it a name, and even if you call it 0, you should know that it's not the same 0 that is in the integers. And this is not the same 1 that is in the integers. This really is a value, mod n, and there is a relation between this and the one in the integers, of course, because it comes to this. But not that this one goes to that. the other way around. Okay? So let me write this. Let me write this clearly. So the mathematical notation for mod n is usually like this. Zn, okay. The this is the notation. Correct relation between Z and Zn is that Z goes to Zn and not Zn goes to Z. There is no such nice thing. Okay, now you will see why and kind of why this is important. Now Z goes to Zn. This is for sure. What do I mean by this? Every integer corresponds to a value mod n. So as a function, this function is clear, right? Do you agree?
Yeah.
Yeah, it's clear.
Yeah, every integer has a value. Well, positive or negative integer, it doesn't matter. Right? Every integer has a value mod n. It corresponds to a unique value. But when we talk about this, sort of inverting this, which is what we think when we represent the numbers like this, which is when we want to think of Zn as a subset of Z, actually this is what we want to do. We want to choose for each value in Zn, we want to choose one value here, one integer, one particular integer, which corresponds to it. And we sort of, as a standard convention, we think that, this range of numbers between 0 to n-1 is the best range. So we want to choose the integer from there. So we represent the values in Zn by these, but this is just one particular representation. This is not an algebraic representation. Okay, so this is what I mean. Precisely when we represent the n values in Zn by the integers, when we use this representation, in fact, we implicitly construct something like this. But this is not an algebraic construction. What I mean is, for example, the arithmetic here is not correctly represented here. That is, if you take Z3, in Z3, if you have 1 and 2, their sum must be 0. But as actual integers, 1 plus 2 is not 0, right? So, but of course, I mean, we don't make a mistake here because we understand what we mean by this representation. So when we really represent the numbers in Zn by this, we understand this is just a representation. For example, one plus two is 0. Actually, we can even write this as equality if we understand what we mean is 0 in Z3. By 1, I mean whatever corresponds to 1, right? Whatever 1 as an integer, and the integer 1 corresponds to some value in Z3. I also denote it by 1. but 1 plus 2 is not 0 in Z. So going from Zn to Z is you are destroying something. But this is not confusing. But this is not confusing. Because we know that this is just a representation. Notice, so far I have not taught you anything new. This is all stuff that you know. But I wanted to lay this background because I'm going to teach you something new actually now. Okay? Actually, something new is coming. But I wanted to sort of lay this background to show you, to demonstrate to you that you, in fact, know that this is just a representation. This is just a representation. Well, in say more rigorous textbooks, they usually instead of choosing integers for a representation like this, instead of such a construction, such a non-algebraic construction. Okay. So let me just take this whole thing as an explanation of. And this whole thing is an explanation that there is no natural way to go from Zn to Z. But going from Z to Zn is natural. So this is why they usually, in rigorous textbooks, they denote the elements of Zn as what are called equivalence classes of Z. So instead of saying that this is 0, they call this itself as a set. Instead of calling 0, they call this the set of numbers which are multiples of n. So 0, n, 2n, 3n, minus n, this whole set, this subset of Z is a single element in Zn. And then the other set, 1, n plus 1, 2n plus 1, 3n plus 1, this whole set is a single element in Zn that we call 1. You see, when you look at it like this, when you consider this representation, then stuff works better than this. That is, considering the more algebraic representation. So this red thing is a representation which sort of tries to attempt putting Zn inside Z. But another way, so instead of Zn to Z, which doesn't work, we have natural map Z to Zn, which motivates the representation of Zn as, so this is the representation. So this is my Zn. Now one element here is this is a single element that we call 0. Now this is the next element that we call 1. And going like this. finally something like this. So this is the one that we call n minus 1. Okay, that's ellipsis here also. You see, for example, Z2 mod 2 has two elements. One element is the set of even numbers, the other element is the set of odd numbers. You can think of it like this. But of course, this is a very complicated notation. So they usually denote it like this. So they say class of 0, class of 1, class of 2, class of n minus 1. And when we talk about this representation, in fact, this is what we mean. This is very sound mathematically because unlike this, this is algebraically sound. Because, I mean, for example, 1 plus 2 is 0 in Z3, but now when you represent them like this, class of 1 plus class of 2. So if this is a whole class, right? The whole set, 1, 4, 7, 10, 13, etc. This is a whole set. If you add this set to this set, you in fact get this set as sets. So there is nothing wrong, right? As sets. So I hope I didn't confuse you. What I wanted to say is this. When I was an Olympiad student, when I opened any textbook about modular arithmetic, I used to see this notation. I used to see that mod n is consists of n numbers which are equivalence classes of the integers. And I always found this, confusing and unnecessary. Why do I, think of a single element in mod n as a whole set? And single element here as a whole set, I will just think of this as, 0, just one representative element. And I will just think of this as 1, think of this as 2. I will just think of them as one representative element, so I will just think of it like this. Okay, this is not bad, because this is not confusing for me. I know what I'm talking about, right? I know 1 plus 2 is 0 in mod 3, but it is not 0 in integers. Okay, no problem. As long as I know what I'm doing, it's not confusing. And it is easier to think like this instead of thinking the whole construction. But later on I appreciated, okay, this is really how abstract mathematics is structured. You want to put everything in a sound basis uh, instead of just referring to intuition all the time. Intuition is very important, and you need intuitive ways of thinking. So I still think like this. I still think like this. This is not wrong. This is not wrong at all. But it's just good to understand that there is this other way of thinking which opens your horizon, which opens your perspective. This is why I mentioned this. I'm not telling you to change how you think. Okay, is this clear? Like, I'm not correcting something wrong. You know something, but I'm just adding a perspective to this. Which okay, why did I do this? Like, why did I do this whole mod n discussion? Because once you understand this kind of horizon, this is not just an abstract, meaningless discussion, but you actually understand even the arithmetic of mod n better. Okay, now I will show you examples of this. How this kind of, once you get used to this kind of thinking, even some other things. So, do you want to say anything about this? Nothing? Okay. Okay, the next thing I want to now say, this is very concrete knowledge which is directly useful in Olympiad number theory problems. That I even personally, I mean, I was a gold medalist, but I didn't know about this stuff. I wish I knew. I learned about this later when I became a trainer. I just learned it by myself basically when I started to look at the Olympiad problems from the abstract point of view. Well, I noticed that, okay, once you understand that it's not Zn that goes to Z, but it is Z that comes to Zn. You understand the independence of Zn, independence of mod n as a number system. And it's just integers that come to this. This is not that it goes to integers. Integers come to this. Other stuff may also come to it. This is not dependent on the integers. It's not part of the integers. It stands out. Integers come to it. Non-integers can also come to it. Some rational numbers come to mod n. And it's not something outside of mod n. It's not some version of fractions in mod n. It's just mod n itself, the same n numbers. There is no more numbers. There is no more numbers. But let me now write it like this. Now, very important concrete knowledge. Much like every integer has a value in mod n. So this notation that I'm writing here, z goes to zn, just means every integer has a value mod n, has a unique value mod n. Some rational numbers also have a value mod n among the same n values, of course. There are no more numbers in the system. Which rational numbers? Any a over b where b is coprime to n. This rational number goes to a unique value in Zn. When you think about this way, you see there is an advantage to this. There's an advantage to be able to see more numbers, rational numbers are actually having a value in mod n. So let's do examples of this. That's let's say, what is 1 over 3 mod 2? What is 1 over 3 mod 2? Well, okay, how do you find it? The way to find it is, this has to be consistent with the algebra, right? This arithmetic, you can think of this rational number as division of two integers. Well, you have arithmetic within the rational numbers. You have division of rational number by rational numbers. So this division arithmetic must be consistent with, much like, as I said, this thing is an algebraic thing, right? when I add two numbers as integers and look at it mod n, it's the same thing as look at them separately mod n and then add them. A plus b mod n is congruent to a mod n plus b mod n. Similarly, a times b mod n, so multiplication here is consistent with multiplication here. Division here must be consistent with division here, as long as it's well defined. There is a certain level of division here. So this is why I just loosely use the term number system without specifying what it is. But it definitely has addition, subtraction, and multiplication, which is consistent, and some division, some. You cannot divide by everything. Well, even in integers, you cannot divide to integers by integers if you want to stay within integers, right? You can do divisibility. You can divide as long as they are divisible. For rational numbers, you can divide as long as the denominator is non-zero. Here, you can divide as long as the denominator is coprime to the mod n, coprime to n, coprime to the mod value. So mod 2, you can divide 1 by 3, but 3 is just 1 mod 2, right? So this is dividing 1 by 1. So this is just 1 mod 2. So let's stare at this and appreciate. Would you say 1 over 3 is an odd number? So I shouldn't keep talking, right? I should get feedback. Let me also write 2 over 3, which is 0 over 1, which is 0 mod 2. How about 3 over?
Isn't it also the numerator multiplied by the inverse of the denominator?
Say it again.
When we have a over b, isn't usually modular a multiplied by the inverse of b if the inverse of b exists?
Exactly, this is what it is. This is the definition of 1 over b. Definition of 1 over b is the multiplicative inverse of b. If it exists, this is what 1 over b goes to. So, yeah, there are two things to say here. Yeah, one thing is to just say, well, this is definition of 1 over b. Because, well, like, for example, yeah, let's continue this as examples. For example, I can say multiplicative inverse of 3 modulo 7 is 5, right? So I can say 1 over 3 is 5 mod 7. Well, you can think of this as definition, but you can also think of this as the actual rational number 1 over 3, which is literally 1/3 of 1. This rational number. It goes to 5 mod 7. This kind of tells us that the difference between this, well, it goes to 5. What does it mean it goes to 5? What is 5 mod 7? Well, it's the place that 5 goes to. So 1 over 3 and 5 actually go to the same value, mod 7, which means their difference must be divisible by 7. So 5 minus 1 over 3, which is 14 over 3, is divisible by 7. Would you say this? It's similarly saying that 2 over 3 is divisible by 2. Can you say it's even? 1 over 3, can you say it's odd? It's not divisible by 2. Do you hesitate to say that?
Isn't divisibility only exclusive to integers?
So, see, this is a perspective opening discussion. This is why I wanted to say it. So it's not wrong to say that divisibility is exclusive to integers if you want to just, think of it exclusive to integers, which is a good setup. But sometimes, well, the whole mathematics, the entire mathematics consists of structures nested within each other. There are structures nested within each other. And sometimes we just concentrate on one structure, one special structure, and work in that setup. Sometimes we work in more generalized structures and sometimes further generalized structures. In every generalization, well, generalizations are good because you work with bigger things, and there is an advantage somehow to work with bigger things, because you have more objects, you have more things to find. But there is also sometimes you lose some information in generalization. Not everything works. In special setups, some things work better. So divisibility is also like this. You can say divisibility is exclusive to integers. Well, okay, and integers, there are very many nice rules about divisibility. Now, you can say, okay, there are more general systems than integers that also have a notion of divisibility. And when you realize this, when you learn about this, you get excited. Okay, there are bigger systems, bigger number systems that have the notion of divisibility, but they don't have all the same properties, all the same nice things about integers, but still good. So generalizations are always okay, you lose some things, but you gain more. You lose some properties, but you gain more objects. So they are good for bringing you more objects, but they are not always preserving all the properties, which means you should still remember the special setup. This is why we have nested structures in mathematics all the time. For example, in number theory, in Olympiads, we really just work with integers. But in mathematics, there is a theory called algebraic number theory. They work with what are called algebraic integers, which are more general than our integers. For example, the complex number I is considered an integer. And then there is a divisibility stuff there. And there is prime factorization stuff. And when you get, when you open the way to the more to greater number of integers, some divisibility stuff occurs. Well, this is another subject. I don't want to enter this, but just to emphasize how mathematics works like this in general. Like 5 is factorized like this, for example. And when you allow this factorization, you say, okay, 5 is not a prime anymore. 2 plus I is prime and 2 minus I is prime. And this becomes the prime factorization of 5. Well, is it wrong to say 5 is a prime number? No, it's not wrong to say, as long as you know your context. So in mathematics, well, in life in general, every statement has a context. The statements are meaningful only in their context. I'm going to erase this because it's not our subject. This is similar to that. So divisibility, we can talk about divisibility as long as we know what we mean. Okay? If we know what we mean, if we can define the stuff appropriately, well, maybe this is not the appropriate definition to say it's divisible, and you will see it's not a perfect definition. Maybe this is so this is why I put a question mark. I should say maybe, but I mean this statement is dubious. Sorry. Well, maybe. But this is for sure. This is definitely, there is no question here. This is mathematically perfect. Okay? So I'll put things like this here. Well, this is okay. This is already not surprising, but this, considering this as the actual rational number, modulo 5 is correct, even if this is not your interpretation. So even if you don't want to say 1 over 3 is an odd number, you should still be able to definitely say 1 over 3 is 1 mod 2. Okay, maybe for you 1 mod 2 is the same thing as odd, right? 1 mod 2 is just another word for odd number. Well, depends on the context. If we are talking about integers, then 1 mod 2 is the same thing as odd numbers, and 0 mod 2 is the same thing as even numbers. But if we are talking in a more general context, 1 mod 2 and 0 mod 2, they are not necessarily integers. They might be fractions like this, and maybe I don't want to call them odd numbers. Okay. Now, this is a matter of definition. How would you say 1 over 3 is odd? Or 2 over 3 is even? Maybe or maybe not. And maybe we wouldn't say it, but similarly here, maybe or maybe not. But definitely this part is for sure. Whatever name you give it to it, you either call it divisibility or something, but this modular arithmetic is absolutely necessary, and this is very important concrete knowledge. It really, we see it in problems like this. Now, this is something about mod n, and there is this is related to maybe something more fundamental than this. Directly, your question opened up a subject at him. How about divisibility in rational numbers in general? Okay, we should maybe first talk about divisibility in rational numbers, and then once we talk about it, this can become even more meaningful. So let's open a new page and talk about divisibility in rational numbers. Divisibility, stuff like GCD, prime factorization, etc. Before I pass to this discussion, is there anything you want to say about this? Okay. So let me put this title here. GCD, etc. in rational numbers. Okay. Okay, the first thing I'm gonna say, okay, what do you know about prime factorization? You know about it in integers, right? Probably know this. Every integer, well, every positive integer, you would say. Every positive integer has a unique prime factorization. Now we can say more. Every positive rational number, or every non-zero rational number, if we can put the plus or minus in the beginning. Every such rational number has a unique prime factorization. Once we allow the exponents to be any integers, not necessarily non-negative integers. And once you realize this is kind of an obvious statement. Much like we know, A equals P1 to the alpha 1, P2 to the alpha 2. For any positive integer A. What are these? Where P1, P2, Pk are primes. And alpha I and negative are integers. There is unique factorization.
Here, shouldn't alpha I be strictly greater than 0?
Oh yeah, let's well yeah, if we write it like this, it is strictly greater than 0. Yes. Alternatively, we can write it like this. Good for catching it. Are integers. But let's say we know let's say we know we all know that there is unique factorization of this kind, or we can say we can also say A equals product of P to the something for all primes. This is the infinite set of all primes. Okay. Infinite set of all primes. P to the power of something, right? Some alpha. Or let me, okay, maybe better way to write it like this. Okay, I mean that's also good, but just for pi to the alpha I, where pk is the kth prime. Here it's not the same notation, so okay, maybe I should use then q1, like yeah, where qi is the ith prime. So what I mean is this, 2, 3, 5, 7, 11, all these primes. So this is q1, this is q2, okay, this is q3, q4, q5, etc. With all the primes. Now I can say I can write it like this. I can write it like this with strictly positive exponents, as you said, strictly positive exponents. Because if it is 0, I can just ignore that term. I may not put it there. I will have finitely many prime numbers. I don't know which ones they are, but finitely many prime numbers with positive exponents. Or alternatively, I can write all the prime numbers there. I can put all the prime numbers there. I don't look at whether the prime number actually divides A or not. I put all the prime numbers, infinitely many of them, and I put the exponents. They are non-negative integers. Finitely many of them are non-zero. With finitely many non-zero. You see, I confuse between these two things. So this is also another way to express prime factorization. So we know this. We can also say it like this. Now we can also say every rational number has this. We also have exactly the same formula. For any positive rational number. Removing the condition. Now there is no such condition. Now they can be negative. Now this is also unique factorization. Well, of course, here also, since finitely many of them are non-zero, you can still do it like this. You can still do it like this. You can ignore the non-zero. You can ignore the zero terms. You can just keep the non-zero. You will have some primes with positive exponent, some primes with negative exponent. You can have that. And this is exactly the divisibility, well, the fraction representation of the rational number. Nothing but that. Right. In any case, I mean, whatever you didn't. So the lesson, prime factorization works. Works in rational numbers. Well, as examples. So this is the lesson that I was trying to say. Well, as examples, just take any rational number, right? Say 30 over what? 77. So this is equal to 2 to the 1, 3 to the 1, 5 to the 1, 7 to the minus 1, 11 to the minus 1. Or let's not go so big, right? Let's just go. This is simply 2 to the 3. I suppose this is clear. Is there a question about it? I mean, it's not about whether we write it like this or write it like this. It's not about that. You see 5 over 8 is 2 to the minus 3. 5 to the 1. And even if this is not simplified, if the fraction is not simplified, you will have the same prime factor in both sides. So in the multiplication, they will cancel each other. So the right-hand side will automatically be simplified, basically. So it's always unique. So unique prime factorization. This is unique prime factorization. Works in rational numbers. Why did I write it like this? This is foreign notation, actually. This is another subject. There is a notation for the exponent for every given any number a and any prime number q. There is a notation. Do you know of it? Sometimes used in Olympiad solutions. It's called valuation.
Yeah, we know that.
Yeah. So this is why I wrote it like this. Well, just note But alpha I is called the valuation of A at the prime Qi. So valuation of A at Q is denoted as VQA. So VQ is the valuation function. VQ as a function, valuation of numbers at Q. So with this, the prime factorization is usually written like this. Let me write it with valuation notation. With valuation notation, we write the prime factorization like this: P to the VPA for all primes P, the set of primes. Here, what is A? For any positive rational number. The same formula. This is a formula that you may have seen. This is basically a definition. This is just writing the prime factorization in this way for integers, but this just holds for rational numbers. So valuation is a function. Valuations are functions. Are functions from where? So VP is a function from positive rationals to integers. But it's also a function from positive integers to what?
Non-negative integer.
Exactly, non-negative integers. Right. Like, for example, V2 of 5 is 0. V2 of 6 is 1. V2 of 8 is 2. V2 of 3 over 2 is minus 1. Something like this. See, this is a great example of how generalization works. Normally, you think of valuation in here for positive integers. When you have a positive integer, it has a valuation which is a non-negative integer. Now you generalize it. You see, you can generalize this to rational numbers, but then you lose something. You lose the non-negativity. But this generalization is good. But now, because you can use non-integer inputs for the valuation function, and this formula still works. But now the valuations could be negative. So this might have some disadvantages, but some advantages. This is how generalization always works in mathematics. We have nested structures. So this is by itself important. This is also important. It's not that, we generalize something and we forget about the previous thing. No. We generalize, but the previous thing is still important. So I can also call it a lesson. Okay? Or not. So how about GCD? And LCM? Well, okay. Depends on how you want to define. So in the context of integers, we have a very nice notion of divisibility that we know. And GCD is the greatest common divisor. And LCM is the least common multiple. But if we can define it in terms of formulas, Give me the formula of GCD AB in terms of the prime factorization.
It will be the product of b to the power of minimum of valuation of a mod b and valuation of b mod b.
Yeah, exactly. So as we know, when we do the GCD of two numbers, when we look at their prime factorization, we always choose the smaller exponent. Right? This is the GCD. So, well, for integers, we already know this. So minimum of these two valuations. Right? In other words, this is the same thing as saying valuation of the GCD is the minimum of the valuations. Well, in some sense, GCD is the function which takes minimum from outside of VP to puts it inside as GCD. By the way, the VP function has this nice property. VP of AB equals VP A plus VP B, right? This is obvious, right? This is actually the property of the valuation function, the main property. Does this property remind you of something? Another function? This is the main property of the valuation function.
The logarithmic function.
What?
Logarithmic function.
Yeah. It's like the logarithm. So this is an interesting thing. It's not a coincidence. So valuation functions are sort of logarithm-like functions in the context of number theory. And GCD is what converts minimum. So valuation converts product to addition. When you have multiplication, it becomes addition, like logarithm. When you have GCD, it becomes minimum. When you have LCM, it becomes maximum. So if you think of it like this way you can have the definition of GCD and LCM for rational numbers. No problem, right? Examples. So let's write it also as a lesson. GCD, LCM work in rational numbers. When we understand them in terms of formula. Well, when we understand them properly, let's say. But maybe not as names. Okay. Well, okay, tell me the GCD of 1/2 and 1/3. So this is an exercise.
It will be one.
No.
Will do. No. 1 over 6.
Yeah, 1 over 6, yeah. So let's prime factorize this. This is 2 to the minus 1, 3 to the 0, 5 to the 0, etc. And then 2 to the 0, 3 to the minus 1, 5 to the 0, etc. So if you take the minimums of this, 2 to the minus 1, because minus 1 is less than 0, 3 to the minus 1, because this minus 1 is less than, the others are 0. 1 over 6. This GCD is 1 over 6. Now, again, would I say that 1 over 6 is the greatest common divisor? Would I say that this is the greatest common divisor of 1 over 2 and
Oh,
1 over 3? Well, would I even say that it's a divisor? Would I even say 1 over 2 is divisible by 1 over 6? Well, maybe not, right? Maybe or maybe not. But if I start talking like this, I will soon notice that I cannot be fully consistent. Because if I want to say, okay, 1 over 2 is divisible by 1 over 6 because the ratio is 3, because it's an integer. Maybe I can talk like this. I can say, okay, I will say a rational number divides a rational number if the ratio is an integer. And this makes sense. If I define it like this, it will be consistent with the notion of GCD. Because in the GCD, I take the minimum of the exponents. So when I divide any of these numbers by the GCD, all the exponents become non-negative. The ratio is an integer. So the greatest common divisor notion seems to be consistent with this. But on the previous page, I had this kind of thing. I had 14 over 3 divisible by 7. The ratio here is 2 over 3. It's not an integer. So I cannot keep talking like this. But talking is another thing, okay? Divisibility. This divides, this divides. So the language is perfectly suitable for the integer setup. As long as we work with integers, we have the language of divisibility. A divides B. We know what it means that A divides B. And we know what it means, what this means in terms of modular arithmetic. So it means B is 0 mod A. It also means that A is a divisor of B. So A will be, for example, if A divides both B and C, A will divide the GCD of B and C. So we know what this means in terms of GCD, what this means in terms of prime factorization. The language is suitable for integers. For rational numbers, maybe we don't really talk about divisibility, but we know for sure this. We have valuation for rational numbers. It perfectly works. So we have prime factorization. And based on this valuation, we have GCD and LCM as formulas. We have prime factorization, GCD, LCM, all based on valuation for rational numbers. The formulas work. And we have modular arithmetic for rational numbers. And as you can see, there is a way to describe this. Which rational numbers have values mod n? We want those rational numbers to not have, in the denominator some factor of n, right? So basically, whenever the valuation, whenever VP of n is positive, we want VP of this rational number to be non-negative. So with that condition, the rational numbers map to mod n. Okay, if the denominator doesn't have a common factor with n, which means that in the prime factorization of this rational number, the negative exponents are not positive exponents in n. The negative exponents in this rational number are 0 exponents in n. In this case, the rational number a over b maps to a value mod n uniquely. The actual rational number 2 over 3, which is like 2/3, 0.66666. This is the actual rational number, okay? It is actually 0 mod 2. So 1 over 3, 0.3333 is actually congruent to 5 mod 7. This modular arithmetic is consistent. Whether I call it divisibility or not, the language may break down, but the modular arithmetic and the GCD and prime factorization works. So lesson modular arithmetics. Mod n, where n is a positive integer, of course, works in rational numbers. So I'm not talking about mod n with rational mode. That maybe there is no such thing, I guess. Probably no such thing. No, that doesn't make sense because mod n consists of n values. What does it mean that you have a set with half, say 1 over 2 elements, right? There is no such thing. The number of objects is always an integer. So mod n, this is always a positive integer, but this works in rational numbers. The arithmetic, the algebra works in rational numbers. So a mod n, when I talk about a mod n, a can be a rational number. But this is definitely an integer. Okay, I wanted to give you this lesson to really bring the rational numbers into the picture of number theory. And this is a very important concrete knowledge, both this in terms of modular arithmetic and in terms of prime factorization, GCD stuff. Bringing the rational numbers into the picture is a very good thing. So for example, there was one Olympiad problem that I saw many years ago, and I used to use that problem in my training. And the problem had a very interesting story. Every time I used it in training, I found a shorter solution. Or some of the students found a solution which was shorter. First, I had a long solution to the problem. And at the end, it ended up with a tiny solution once I understood this stuff about rational numbers. An Olympiad problem. Let me write this one to you. I will not I don't want to waste time on this problem because we have other problems to work on, but maybe it would be good to work on 5 minutes at least to warm up to the problem. So D1 and D2 are divisors of n, okay? These are integers. Everything is about integers in this problem. There is no rational numbers in this problem, okay? Olympiad problem. So let me write D1, D2 are divisors. Are two divisors of n, such that somehow this relation turns out to be correct. GCD of D1 with n over D2 equals GCD of D2 with n over D1. As you notice, these are just integers and this is a regular GCD, okay? Because this is an Olympiad problem. In the Olympiad problems, they will not... well, this stuff about rational numbers is considered outside of the Olympiad subject, but actually when you solve it, you can use it. Such that the questions show that D1 equals D2. Just try to solve the problem as you normally would solve it. Normally, how would you approach this problem? How would you try to solve?
I would assume they're not equal and have D1 be bigger than D2.
Yeah, something like that, yeah. Yeah, and then from there you will try to find that these GCDs are not equal, yeah. Yeah, work on this at least 5 or 10 minutes.
We can just multiply both sides by D1, D2.
Yeah. Okay, you can do the prime factorization of D1 and D2.
We can do it by the GCD formula. We prove that we assume for quantity that VB of D1 is bigger than VB of D2 for some prime D, for some prime B, and then we reach a contradiction.
No, we can
Yeah.
just multiply by D1 and D1, D2.
Yeah, okay. I know what you both mean. Okay, let me just write these solutions like that. So solution 1 is to just look at this with evaluation of a prime number. So this says minimum of VP D1 and VP of n over D2, which is n, VP of n minus VP of D2 equals minimum of VP of D2 with VP of n minus VP of D1. From there, we can show that these are equal, because if this is less than this, then this is also less than this, basically. Well, in fact, the difference between this and this is the same as the difference between this and this. So, okay, well, one way to complete this is to write it like that, if VP D1 is strictly less than VP D2, then VPN, so this term is also strictly less than this. Then this would be a contradiction, because the minimum of these two would be strictly less than both of these. So it will be strictly less than the minimum. So this would be a contradiction. Similarly, the other way around, it would be a contradiction. You can solve it. You can write it like that, or you can alternatively say well, let me write this 1a. You can finish the problem like this, or you can finish like, you can say, look, the difference between this and this is the same as the difference between this and this, so therefore the difference between the minimum is also the same. This minus this is equal to VP D2 minus VP D1, because this is equal to, right? If I have x and y, if I have x plus k, y plus k, then the difference must be k. Because this is the same difference. So this automatically solves it because this difference is 0. So this VPD2, VPD1 equals VPD2. Or as a second solution, you realize that, well, what you do with VP, you don't have to do it with VP. You can just do, well, it's basically, if it is just this idea, then you can do this with GCDs directly. Namely, the ratio of the GCD of D2 n over D1 over GCD D1 n over D2 equals D2 over D1, which is this ratio. Now notice this is a very good thing. When you understand rational numbers, this works. This kind of works better. Because if this is the ratio, if there is the same ratio between these two and these two, it must be the ratio of the GCDs as well. Now, this is the perfect solution. But alternatively, once if we are not very comfortable with rational numbers, we could see this like that. We could see GCD of D2 n over D1 equals GCD of D2 D1 with n divided by D1. If we are just only comfortable with rational numbers, only comfortable with integers, we can see it like this. Adham, was this what you meant? Or did I not understand correctly? So what was what you meant, Adham?
Yeah, then they're forced to be equal.
Yeah, if we are only comfortable with GCD in integers, we would do it like this. But this is sort of making it longer. This is the perfect solution.
Can you explain solution 2 again?
Which one? The first solution to the second solution?
Solution 2, the second one.
Yeah, this one, this one. This.
2, the solution 2.
Yeah. So this is solution 2, this is solution 2 prime. Okay. Solution 2 is essentially this formula. So more explanation. Well, okay, let me write the explanation here. So for better explanation, I want to say I can talk about a formula like GCD, well, general formula. General formula GCD AX BX equals X times GCD.
Oh, yeah. I don't mean the 2 prime. I mean solution 2.
Yeah, this is solution 2. This is solution 2 because this formula even works for rational numbers.
Oh, okay, I see. So you did it immediately. Okay.
Yeah, I did it immediately.
Okay.
So here in this case, x is d2 over d1.
Yeah.
This is A, this is B, and the ratio is d2 over d1. This is why I'm saying like this is the perfect solution. It's actually the same solution, but this is adding a step because of not thinking about not being accustomed to rational numbers. And this is just the valuation version of the same solution. What you do with GCD, you can do with valuation. And everything that division, whatever division you have here, it becomes subtraction. Whatever multiplication you have, it becomes addition. VP is like logarithm. VP is like logarithm. It converts your argument, your proofs with division and multiplication to proofs with addition and subtraction. Subtraction and addition. Yeah. So this is what I wanted to show here. All right. So let's now let's now do what? Before solving the shortlist problem, let's solve the problem that well, I didn't give you enough time on the shortlist problem. I gave you about half an hour, but okay, I will discuss it a little bit. Then wait, what happened? Abdullah has a question, right? What is your question, Abdullah?
Oh, no, it's okay. It's okay.
Okay. So let's look at this problem. These are rational numbers. We add them, and it's an actual fraction to show that a is divisible by p squared. Let's first work on this problem. To familiarize ourselves with this arithmetic of rational numbers. So in this whiteboard, when I open new pages, does it not automatically open on your screen? Do you have to open it yourself?
Yes.
This is how it works. Okay.
You can follow him where he writes, and it will automatically switch.
Okay, I didn't understand, but all right. I mean, so all of you are seeing this problem, right? I just saw the discussion in chat that you had. So any information about the problem? Anything that you have found? Any partial result?
It's a famous theorem. I already know it's proved.
I already know it's
Yeah.
proved. Okay. All of you
Yeah,
know?
same here.
Oh, okay. You should have told me. Okay, I wouldn't wait.
Isn't it Wollston's theorem or something like that?
I honestly don't know the name, but what is important is the proof.
We can solve
but-
it using inverses, then the formula for the sum of squares.
Yeah. So this is the proof that I was gonna mention as well. So okay. So solution. Well, first of all, I want to indicate that the partial version of this, the easy version, that P divides A, we can prove it easily in two different ways. One way to prove it is to pair up these fractions. 1 plus 1 over P minus 1 is P over P minus 1. 1 over 2 plus 1 over P minus 2 is P over P 2 P over 2 times P minus 2, and we can add that. Well, A over B. Let's write it like this. So this is equal to what? Summation of P over K times P minus K. K goes from P times this sum. Now, whatever this is, let's call this X over Y. Clearly, Y is not divisible by P because Y, the denominator, comes from these denominators. Comes from the product of these denominators, which is none of them are divisible by P. So this shows that well, A over B equals P times X over Y. So there is no cancellation here. A is P times X and B is Y. So this is one way to show that at least A is divisible by P easily. Another interesting way to show that A is divisible by P is to directly look at this fraction modulo P. Now, each of these fractions, each of these rational numbers, 1, 1 over 2, as you notice, these are the actual rational numbers and we are adding them as rational numbers. So this is true rational number arithmetic. But we can look at this modulo P. All of these numbers have a value modulo P. There are P minus 1 numbers here. P minus 1 rational numbers. And all of them are different modulo P. It's easy to see that they are different. If K and L are different, then 1 over K and 1 over L are different. P minus 1, different numbers, different non-zero numbers. All of them non-zero, different P minus 1 numbers modulo P, which means this is the full class of numbers modulo P in some permutation. There's some permutation here, but these are the same as 1, 2, 3, P minus 1 modulo P. So this summation is equal to the summation 1 through P minus 1, which is 0 mod P. So this fraction is 0 mod P. A over B is 0 mod P. Now, do we say that A over B is divisible by P? Maybe we don't say that, but A over B is congruent to 0 mod P definitely means that the numerator is divisible by P. That's for sure. Right? This I verbally explained. I didn't write this, but this will form the idea. I mean, if you show that P divides A in this method rather than this method, it it inspires the idea to continue the problem after this point, because now we know A equals P times X, and we want to show that X is divisible by P. Because if we want to show that A is divisible by P squared, we want to show X is divisible by P. So we can focus on this fraction, and we can do the same there. So this is step 1 of the solution, and the step 2. In step 1, I didn't do anything mod P. I just did calculations in rational numbers. But in step 2, I am doing mod P. This fraction, so some of these fractions, if I'm looking at mod P, so this is minus K, this is minus K squared, so minus 1 over K squared. So now what do I have? I have the same fractions like this, but only half of them, up to half of them, but I have squares of them. So I have P minus 1 over 2. I have half of the non-zero numbers. They are squared. So these half of the numbers are different from each other, but are their squares also different? Well, if X and Y are different, and if X is also different from minus Y, then their squares will be different. Because for the squares to be the same, mod P, if X squared and Y squared are the same, mod P, they either X and Y must be the same, or X must be minus Y. And here you can notice that these half of the numbers, the first half of the numbers that we have here, 1 over K's, they are also different from minus of each other, because their minuses are in the other half. So these squares are different. So this forms the full class of squares. In other words, let's put it like this. So this is mod P. Note that these rational numbers, instead of looking at the rational numbers above there, let's look at this one. 1 minus 1, 1 over 2, minus 1 over 2. When I look at these rational numbers, I mean the actual rational numbers, actual negative number, this. These are different mod P. This forms a full class. Forms the full class of non-zero values. Because not only 1 over K is different from 1 over L, but 1 over K is different from 1 over minus 1 over L as well. 1 over K is distinct from, so we should explain this, because 1 over K is distinct from 1 over L, and 1 over K is distinct from minus 1 over L mod P. Well, this is true, I mean, for this K and L in this range, right? So the squares here, so 1 over K squared is not only the square of 1 over K, but it's also the square of minus 1 over K. So these are the squares of all the values, but just taken once. Here, if we take the squares of all the values, it will be twice this sum. Right? So this indicates that sum of 1 over K squared, K goes from, this is half of modulo P. I can say this. Since P is not 2, I can do, half. modulo P. No problem. This goes from 1 to P minus 1, modulo P. Now this thing, as an actual number, this is equal to P minus 1 times P times 2P minus 1 over 6. But since P is also greater than 3 in this case, we can think of this as a fraction. We can divide by 6 modulo P. And this is 0. So this is 0 divided by 6. This is 0. So in fact, we used that P greater than 2 in the very beginning. Because for P equals 2, we cannot even match up. Cannot even pair up the things. And yeah, also here we are using it, of course. Well, we don't even have P minus 1 over 2 when P is 2, right? But now here we are using that P is greater than 3. Is this the proof that you know as well? So just for the sake of completeness, let's say, since this is 0 mod P, it means x minus y is 0 mod P, x over y. So this means x over y is 0 mod P. So P divides x. So P squared divides A, which is Px. Is this the proof that you know, or you know some other proof?
Yeah, it's the one I know.
Yeah, it's the same one. All right. So we can go to our shortlist problem. What do we do in this problem? In this problem, we want to find a sequence of values modulo P. Okay, in the problem itself, we want to find them among the actual integers from 1 to P minus 1. But the condition on them is just divisibility by P. Therefore, we should seek these values among the values mod P in the abstract sense. In the abstract sense, if you find these values, distinct values mod P, automatically each of them has a representation in this range, and they will be distinct numbers. Because if they are distinct mod P and they are in this range, well, if they are distinct mod P, then they are distinct numbers anyway. And they will satisfy this divisibility. So we are really interested in not really finding the values specifically among these integers, but we are interested in finding the values mod P, distinct values mod P, which satisfy these conditions. So this is the inspiring thought. It doesn't sound very inspiring, but if you really understand what mod P means, this is very inspiring. It almost trivializes the problem. Inspiring thought. We are looking for in ZP, in mod P, with the conditions. Yeah. We can now write this as equality in ZP. I mean, the sense of equality in ZP is this, is congruence, right? We are looking them as values mod P. Does this give you an idea? After all of our discussion, you know, when I solve a problem with you, I don't just want to solve the problem, but I want to put it in the context, right? This is what I said in the beginning of the lecture.
Yeah, so we're not really limited to integers. We can use rationals.
Yeah. we can use rational numbers as long as they are defined mod p, well, as long as their denominators are not divisible by p. And what is p? We are choosing p, right? So we can choose p so that the denominators are not divisible by p. So we can just choose rational numbers, and we will choose some p, which is big enough that the denominators of those rational numbers are not divisible by p. So all of them, also the numerators are not divisible by p. So they all will be non-zero values in ZP. Somehow we need to ensure that they are different mod P. And we need to ensure that they satisfy these relations, mod P. Because I mean, when I look at this problem, okay, when I read the problem, I immediately think, okay, I'm looking for numbers mod P. I understand this. I'm looking at these numbers mod P, which has to satisfy these conditions mod P, and they have to be distinct, and I'm trying to find the numbers. But even I mean, even after so much experience teaching this stuff in modulo P, even it didn't come to my mind that, I'm not limited to integers. It didn't immediately come to my mind when I was working on this problem. Somehow it really not something that you can appreciate immediately. But once you think of this idea, okay, let me try to find rational numbers which satisfy these conditions, mod P. It would be easier to find the rational numbers because I mean they don't have to be integers, right? It would be easier to find them somehow. Would it be easier actually? Maybe it wouldn't. I mean, maybe it's just complication. But maybe
But I have a question. How could we make sure that this rational number will be distinct mod B?
well, we will choose P, right? So we will choose the rational numbers and we will choose P. I mean, for example, well, for any two numbers, if they are not the same number, they will be distinct mod P. For sufficiently large P, they will be distinct. Because their difference, well, if a number is not zero, if a rational number is not zero, it will be also non-zero mod P for large P. Because P will not, for large P, it will not divide the numerator of this rational number. So it will be non-zero mod P. Similarly, if A and B are distinct, B minus A is non-zero. It will be non-zero mod P. So B and A will be distinct mod P. But of course, here we are choosing the prime number and the rational numbers together. So if we can first choose the rational numbers and then choose the prime number, this is easy. This would be easy to do, to make them different and to make them non-zero and different, because you can just choose the prime number sufficiently large and that's it. But the problem is you want the rational numbers to satisfy this condition mod P. So you cannot just choose it sufficiently large, right? Or can you? By the way, regarding the previous problem, Kerim says you can also show P cube. P cube divides A. For
I remember there's being a problem similar to this.
yeah, but I think it's a different one because in this one I tried until 11 and it doesn't divide. The P cube doesn't divide. For 5, 7, and 11 it doesn't. But there is a problem with P cube divides. It's this one. that I remember.
Yeah, probably a variant.
So 2p, choose p, I think. Another related one.
Mhm.
I think 2p, choose p is congruent to 2 mod p cube or something like this. But probably I remember correctly. Well, 10 choose 5 is this is equal to 63 times 4, which is 252. So yeah, 252 minus 2 equals 250, which is, you say 5 cube. Well, I probably remember correctly. I think this is the one that you mean. Or is there another one? I probably remember correctly. But we must check.
I think I saw something like this before.
Something with fractions?
Isn't
This 2p choose p.
doesn't this fail for p equals 2?
No, for p greater than or equal to 5, similarly.
Okay.
Well, the idea is here, the idea is you can, well, we can even try to prove because 2p choose p, this is equal to summation of pk squared. Well, 2n choose n equals summation of nk squared in general. This is the formula. So p choose 0 squared and p choose p squared gives us this 2. So 2p choose p minus 2 equals p choose k squared. And k goes from p to p minus 1. So this is equal to p squared times what? P minus 1 factorial, k factorial, p minus k factorial squared. This k goes from 1 to p minus 1. So somehow we just need to show that this is divisible by p. Because this is a fraction. This is no, well, in fact, there's an integer, but we can even cancel the common factor p minus 1 factorial and look at this as a fraction. We must show this is 0 mod p. So since this is a common factor, what is really interesting is to show so 1 over k factorial p minus k factorial squared. This k goes from 1 to Well, you don't even need p minus 1, right? You just need p minus 1 over 2 half of it because it becomes the same thing. 0 mod p. And this is probably correct. Somehow it can be proven along the same lines, I guess. Proof attempt. Anyway, let's go back to our original problem. And with this, we can finish the lecture. So, is there a way to somehow first choose the rational numbers and then choose p? I first choose the rational numbers in a way that, these conditions are gonna be automatically satisfied. Not p. I mean, this product will be equal to I in mod p anyway. Can I do that?
We can define the sequence recursive.
Yeah. The sequence of what? Sequence of rational numbers?
Of the rational.
Recursively, according to what?
We just choose A1 and A2 and A3 and A4 such that their product is 1.
Their product is 1 in the sense of...
Irrational numbers, as rational numbers.
Yeah, exactly 1. Actually 1. Yeah. That's what you mean. Okay. As rational numbers. All right. And then for A5?
We define A5 to be 2 over A2 times A3 times A4.
As equality, right? So basically what you're saying is, okay, we want to choose the rational numbers so that these are actual equalities in rational
Yeah.
numbers. If there's an actual equality in rational numbers, it will automatically hold for in mod p for any p. So it will not be an obstacle for me. So this is the inspiring thought 2. This is inspiring thought. Inspiring thought 2. Let's choose rational numbers. Maybe let's use a different notation now. Or maybe not. I mean, let's choose rational numbers A1, A2, AK3, such that, well, positive rational numbers. Right. Well, they don't even have to be positive, but it's just this condition. Yeah. This is actually I. Then after choosing these rational numbers, I can just choose P if these rational numbers are distinct. If the rational numbers are not, if 2 of them are the same, then there is no way I can choose P to make them different mod P. They are the same number. But if they are distinct, then I can choose sufficiently large P and they will just be distinct non-zero numbers. And this condition will automatically be satisfied because it's satisfied as an equality. So let's choose distinct. So I will ignore positivity again. Distinct rational numbers, distinct non-zero, right? Yeah. Well, they're automatically non-zero, right? Distinct rational numbers, such that this is the case. this will finish the solution. So what we really need to prove is that we can do this, and this defines the sequence recursively. But we need to show that they are different. They are in fact distinct. So to study this defines the sequence recursively. Once we choose A1, A2, A3. So we just have to choose A1, A2, A3 carefully so that these numbers are all distinct. Now, notice the problem has not finished because we have to show that we can do this. We must choose this carefully so that the sequence, so that the recursively defined sequence consists of distinct rational numbers. I mean, for example, in fact, this recursion is simpler than because the product of the previous three numbers can already be determined in terms of the number prior to that. So A5 is, for example, determined in terms of A1 only, because A5 is determined in terms of the product of A2, A3, A4, but their product is just 1 over A1. So A5 is really just 2 times A1. So think about this one. So yeah, once you do this, the solution will finish. But so you need maybe another 10 minutes for this. Choose A1, A2, A3, and investigate this recursion. Find the formula for all these rational numbers by investigating the recursion. Notice the problem itself is very easy. We didn't spend time on the problem almost. We just spent our entire lecture time on discussing a number theory subject. We learned about it, yeah, and inshallah we learned it once and for all. But this is a problem, this kind of a problem just appears all of a sudden. And once you are in the right mood of thinking, once you get the right inspiration, the problem becomes trivial. Otherwise, you can still solve it. I mean, even if you don't really think about rational numbers, you will do lots of things which essentially comes down to the same idea, but you will have lots of more pain. Because you will not be able to think of these as equalities. Thinking of rational numbers helped us to think of this as actual equalities and to not worry about P anymore. And P will just come at the end. But somehow you can, even if you don't know about rational numbers mod P, you can essentially do the same idea in an equivalent way. With lots of more pain.
I think that we can get that k plus 1, that a sub k is k plus 1 over k times a sub k mod 4. like I mean
Yeah,
A
yeah.
and the
A
indices.
sub k minus 4.
I mean K mod 4. Like the
But
indices
then not
in
k over k plus 1, then you need k over k plus 1 and the next thing also, right? I mean, recursion gives this recursion gives a k equals k minus 3 over k minus 4 times a k minus 4, I think.
yes, I think I did a mistake.
Because,
But
yeah. Because k minus 3 is a k minus 3, a k minus 2, a k minus 1, a k, k minus 4 is a k minus 4, a k minus 3, k minus 2, a k minus 1. So when you divide this, you get a k over a k 4 minus 4. Yeah?
maybe you can express A sub K in terms of A sub K mod 4. Like the indices,
Mhm.
the indices.
Yeah,
the
I mean,
index
yeah,
of
let's explicitly write like this. For example, well, we can write them in 4 different lines, right? So we can write, we can make a table like this: A1, A2, A3, A4, and A5, A6, something like this. I mean, let's do a table of like this: 1, 2, 3, 4, 0. What I mean is this is the table of I'm just using a notation like this. I can call this M, call this J. So N is for M plus J. I am writing N as for M plus J, okay? J is so N goes as 1, 2, 3, 4, 5, 6, 7, 8. So this is the table of AN. Table of AN with N equals for M plus J. So this is the value of A1, whatever it is. This is A1 times 2. This is A1 times 2 times what? So this is A5. Let me be. So A1. So A5 is just 2A1. The next thing is A9. A9 is 6 over 5 times 2A1. The next thing is A13. This is, can you tell me? I guess, yeah, 10 over 9 times 6 over 5 times 2A1. So, okay, this becomes clear that whatever A1 we choose, this is an increasing sequence, because every time it's multiplied by something bigger than 1. So these numbers will not be the same. Similarly for A2, A6 equals Can you tell me?
I think 3 over 2 sub 2.
Oh, yeah, 3 over 2, A2. A10 equals 7 over 6. 3 over 2.
Actually, I think that we don't have to find some formula for A sub k.
Really, why?
I think that
I mean, yeah,
like
maybe we don't need to find the formula. What we need is to show that they are not the same, right?
yeah, we can like just look at all the elements that their indices are congruent to 1 mod 4. It's obvious that they are all distinct because the coefficient that we multiply it by A sub 1, it's varying.
So, I mean, if I look at a line, if I compare these numbers among themselves, yes, they are different because every time I multiply by something bigger than 1. This is the important thing. I
Yeah.
multiply by something bigger than 1, so it's increasing. So this is an increasing sequence. So these numbers
but
are similarly, this is an increasing sequence. But now I need to show that these numbers are not the same as, so a number from the second line is also not the same as number from the first line.
Yeah, but now we can choose like for A1, we can choose some prime B such that the valuation of A mod B of A1 mod B is bigger than 0, and we choose B like sufficiently large.
Sorry, what is bigger than 0?
I mean, we can choose the some prime Q1 such that the valuation of A1 mod Q is bigger than 0.
But that means you are choosing some divisor of A1, right? I mean, you are
Yeah,
choosing a prime number which divides, so at which A1 is congruent to 0 mod Q.
yeah, and we choose
But we
Q
don't
like
want that. We want these numbers to be non-zero mod P.
Yeah, but Q is like a new prime other than B.
Oh, okay.
I mean Q1.
Okay.
Then we can choose Q1 such that Q1 sufficiently large such that it's not a divisor of any coefficient of any elements in any line. And also it's not
Okay.
a divisor of A2 nor A3 nor A4. And the same thing we do with A2 and A3 and A4. We define a new prime divisors of them.
But we have a condition that A1, A2, A3, A4, their product is 1. So we cannot do everything we can do this for 3 of them, but not for the fourth one.
Like why we can just why we can do that?
Because you will just choose 3 numbers and the fourth one will be automatically chosen. This is equal to 1 over A1, A2, A3. Oh, but maybe you can still do that.
I think we can do. Like if we choose some prime Q that divides Q4 that divides A sub 4, and maybe
So you want to
then we
choose,
can
okay, you want to choose a prime which will not be divisible by the denominators here, so that it doesn't cancel, right? So it will not be it will be not divisible by, it will actually have some very big prime, right? It will be bigger than 5, 9, 13, 17, all of them, and also these numerators 3, 7 something. So if you start with that prime value here, all of these values will be 0 mod that prime, but these will be non-zero because you chose A to be distinct.
and so all of them are distinct.
So you choose one prime for this, another prime for this, another prime for this, and then maybe you don't even need to choose for the fourth one, because At the end,
can
you are
choose,
trying to make them different, right?
you can choose for A sub 4.
But maybe you don't have to, because all you are trying to show is that the numbers in this line are different from the numbers in this line, and the numbers
Yeah,
in this
for
line, and the numbers in this line. So when you are comparing the first line to the other lines, you will use this prime. When you're comparing the second line to the other two lines, you will use the second prime. When you're comparing the last two lines, you will use the third prime.
No, we can just we want to compare the first line with the three remaining lines, and the same thing for the second line, and the same thing for the three line, and the same thing for the fourth line.
Yeah, I mean, it's the same thing as I'm saying, right?
Yeah, but we can actually, I think we can do.
So you are saying in any case you can even choose a fourth prime number, even if you don't need to. You can choose a fourth
Yeah.
prime number for the fourth line, right?
Yeah.
By putting it in the denominator, it will not matter. Yeah. Okay, then we can in fact choose these then as so like Q1 over Q2, Q2 over Q3, Q3 over Q4, and Q4 over Q1. If you choose the numbers like this with those prime numbers, it will be like what you're saying.
Yeah.
Okay. So the idea, okay, solution. See, after some
And
thought, the solution came. So A1,
yeah.
well, yeah, let's choose, well, for Q1, Q2, Q3, Q4. These should be distinct prime numbers bigger than K, basically. Because these
Yeah.
numerators and stuff, they go up to K. Distinct prime numbers. Distinct 4 prime numbers. Let A1 equals Q1 over Q2. A2 equals Q2 over Q3. A3 equals Q3 over Q4. Then automatically A4 equals Q4 over Q1 because of the recursion. Because of recursion. And in general, A4M plus J equals, by this kind of formula, 4M plus J over 3 over 4M plus J over 4 times 4M minus 4 plus J. So I will have M terms like this. Well, as you said, we don't need a formula, precisely speaking. This is just how I write it. J plus 1 over J, A, J at the end. Okay. Here J is 1, 2, 3, 4, where J is like 1, 2, 3, 4. for any number bigger than this, I bring it to this. So this will show, since Q1, Q2, these are large. So when, for example, J is 1, this is Q1 over Q2, and none of these denominators cancel Q1 because Q1 is large. Right, this shows that valuation of Q1 with A for M plus J equals non-zero if and only if J equals 1. But considering that this is for M plus J, so with for example, when we put J equals 2, we have Q2 over Q3. So in the numerator there is no Q1 coming. So we need Q1 to be just bigger than these. So we have to write this precisely, that as long as Q1 is bigger than, which it is, because we chose Q1 to be greater than K. So let's write it like this: as long as 4M plus J minus 3 is less than or equal to K, which is less than Q1. Is this statement precise to you?
Yes, it's precise.
Yeah. And the same thing holds for Q2. So we can even write this. We can even write this generally, but let's not do it. If and only if J equals 2. Good. So the initial choice was important. The initial choice is not trivial. We really carefully chose the initial numbers in a way that's related to K. I mean, we just choose them as big as possible. But if K is not limited, then this will, I mean, at some point this will not work. Whatever initial numbers you choose, for sufficiently large K, you will hit them. But if K is limited from the beginning, you can choose your initial values, the initial primes, sufficiently large, so that these valuation formulas will continue to be correct. So we have these 4 distinct prime numbers, and they distinguish. Q1 distinguishes the first line by looking at evaluating VQ1 at all the numbers. We see the first line is non-zero, fully non-zero, well, positive, in fact. Well, in fact, 1 even, right? VQ1 is in fact 1 on the first line. And well, non-zero is not right. Positive. because it's also non-zero here on the last line. It is -1 on the last line. Yeah. See, I did something wrong. Now I have to fix it. I should say positive. Well, I can also say equals 1, right? So if and only if j equals 1, so if and only if we are on this line, the valuation of VQ1 is 1. 1, 1, 1, 1, 1. And on this line 0, 0, 0, 0, 0, 0, 0, 0, and -1, -1, -1. And if when we look at valuation of Q2, we see -1, -1, -1 on the first line, 1, 1, 1 on the second line, 0, 0 here, and 0, 0 here. So this shows that all the lines are distinct. This shows that A for M1 plus J1 is distinct from A for M2. Well, let's say if these are equal, if two values are equal, this implies they are on the same line. But now on the same line, we have increasing sequences. So this is the valuation argument. And secondly, you need the increasing sequence argument. Plus J strictly greater than for M2 plus J if M1 is greater than M2. So it is a very nice and neat way, and not a hard way at all, to ensure that we don't even have to do anything to ensure that the numbers on the same line are distinct from each other, because it's a strictly increasing sequence. But just to ensure that the numbers are distinct from each other from the different lines, we had this nice, neat valuation argument with sufficiently large primes. So now they are all distinct. So this shows A1, A2, A, K plus 3 are distinct non-zero rational numbers. Now we can choose sufficiently large P. Just for sufficiently large P. Since these are actual non-zero rational numbers, they will be non-zero mod P. And they will, since they are distinct non-zero, distinct rational numbers, they will be distinct modulo P. For sufficiently large P. Because when we evaluate the difference between them and look at the numerator, if the prime is bigger than that, for sufficiently large P, these correspond to. The important thing is that P also doesn't divide the denominators of this, so that these are well defined. Yeah, since P is sufficiently large, these correspond to distinct values mod P. Distinct non-zero values mod P. And then the equality that we have the actual equality that we have here becomes mod p equality, because we replaced all the rational numbers by their mod p equivalents. Okay. Well, instead of writing solution, let's write conclusion, because this is part of the solution. What we did above is already part of the solution. I don't want to write a solution because I want to use the word solution for when I write it formally, analysis of the problem. This is analysis of the problem that I am doing here, and this is conclusion of the proof. All right. I think it's enough for today. Inshallah, I will see you after the Eid.
Okay.
So I want to continue like this, basically, inshallah, as much as I can after the Eid, solving shortlist problems with you. Do you have any question that you want to ask?
No, thank you.
You're welcome. All right, then I'm ending the meeting. See you all